This is a 5-part complex number review, so you can use whatever part you feel is appropriate for where you're at in your understanding. And so this would be 1 of 5. The square root of -1 is an imaginary number. At least that's what Descartes called it. It has a symbol I for imaginary, or the one I prefer, J. They both mean the same thing. And often I put a bar over it just so that you realize that it is a complex number. So I or J, and by definition, it equals 1 at an angle of E to the J, or I, 90 degrees. That's the definition of a unit vector along the imaginary axis. So if I were to create a j omega axis, like so, and a real axis, like so, then the unit vector that travels up the j omega axis at an angle of 90 degrees would be e to the j 90, as shown. It has no real part. You could think of any e to the j theta as being equal to, or theta is an angle, as equal to the cosine of theta plus j times the sine theta. Now, if theta is 90 degrees, then e to the j 90 is going to be equal to the cosine of 90, which is 0, plus j sine theta, which is 1. So then that equals j, or e to the j 90. So 90 degrees is a unit vector pointing up. If theta was 0 degrees, then you would end up with sigma, a purely real number, along the x-axis. This is a simple review. And so, once again, we give a unit vector along the imaginary axis is 1 e to the j 90, and realizing that complex numbers are vectors. They're vectors, but we call them phasors because they're vectors in the complex plane. So they're plotted as line segments from the origin to a point on the complex plane. That point, as a complex variable, is often called S. And so a complex variable S, as a complex number, has a real part, sigma, plus an imaginary part, given by the j, and we call the imaginary part omega. Real part, imaginary part. And are often designated as a bar. So in transfer function analysis, a pole would be designated by a line from the imaginary axis, a pole, to a point x. In other words, you're looking at the bottom of the pole. And that would have the designation P with a bar over it. And once again, like the symbol S, it would have a real part, sigma, and an imaginary part, omega. So whether you're using S or whether you're using P, they both represent complex numbers. And realizing that in the real world, if the complex numbers are going to have meaning, then complex numbers off the real axis always have conjugates. So for every pole P, there's always a P star. And the P star simply changes the sign. So P star would be a sigma minus j omega. So for a more complete analysis, for your pole here, as shown here, for this pole, which is a phasor drawn from the origin to that pole, its magnitude is called omega sub n, the natural frequency. We call this natural frequency. The pole has an angle theta, with the real axis measured counterclockwise as shown from a line drawn from left to right. The damped frequency, or omega d, is the imaginary part of the pole. And so in controls analysis, we say that the complex pole P is going to have a real part sigma and an imaginary part called omega sub d, where d stands for damped natural frequency. That's the frequency that we are going to observe in practice if this system were to oscillate. The complex conjugate would be P star. It's located as a mirror image across the real axis, and we would just simply change the sign on the imaginary part to make it P minus P star. So in control courses, complex numbers will always come in conjugate pairs. Angle theta is fixed in the complex plane, but represents a function. If converted back into the sign, it represents a function theta of omega dt plus psi, where psi is the phase, what we call the phase angle of the function. Now there's some important fundamental relationships using the poles and zeros. So if I have a pole that's up the j, this is the j omega axis, and here's sigma, real, and if I have a pole P out here, as shown, then the magnitude of the real part plus the imaginary part is simply sigma squared plus omega d squared, and we already said that we were going to call that omega n. So sigma squared plus omega d squared square root would be the natural frequency, the magnitude of that phasor, and that phasor would have an angle e to the j theta. Or sometimes this symbol is used for the angle sign. So here's the magnitude, omega n, and the phase angle is shown in the angle condition, or it's shown as e to the j theta. The notation is the same. Note that if I add the pole to its conjugate, so if that's P up here and then I draw its conjugate P star, if I add them vectorially, I'm going to get a distance vectorially. This is going to be 2 sigma, right? Because the real part of the pole is sigma, and if I add these vectorially, I'll get 2 sigma for P plus P star. Similarly, if I were to add P and minus P star, I should say, minus P star goes to the origin, then P minus P star will be a vertical phasor, and it'll have a length of twice the imaginary part. So that'll be twice the imaginary part, and it'll be 90 degrees. So 2 omega d e to the j 90 degrees, or 2 omega d j. And P star minus P will be the complex conjugate, or minus 2 omega d j. And again, the angle is omega dt plus psi in the time domain if we were to transfer that back into time. If you were to multiply both these phases together, then you'd have the one phasor magnitude times the other one, and we know we just multiply them together, so you'd get omega n squared, and the angle, the positive angle, when multiplied, the angles are added, so I have a plus angle and a minus angle that would cancel each other. So the product of the two poles that are complex conjugate is simply the magnitude squared. You could get the Euler identities from mathematics from using these phasors. So we can see that if this is e to the j theta plus e to the minus j theta, which is the same magnitude with the negative of the angle, that I'm going to get twice the cosine of theta, or the Euler identity e to the j theta plus e to the minus j theta over 2 is the cosine. Similarly, if you added e to the j theta to minus e to the minus j theta, then you would get twice the sign, right, along j. So you'd get 2 sine j, or you would get e to the j theta minus e to the minus j theta over 2j equals the sign. And these are the Euler identities, which you may have seen before. This ends part 1 of 5 of the introduction. If you need more help with complex numbers, then go on to part 2.